Welcome to another physics coaching video. I'm Phil Noonan, and today we're looking at a problem that you might strike this week if you're in year 11. This week you'll be doing your Unit 2 exam, almost certainly, and you'll almost certainly have a problem related to rotational equilibrium, or should I say static equilibrium. Actually, that's a good place to start. I've got a sample problem there I'm showing. Static equilibrium just refers to a structure that's not falling down. In fact, it's standing up. So the sum of the forces equals 0, and also the sum of the torques equals 0. They're the two things we can focus on, all right, for a structure to be in equilibrium. So we'll solve it by demonstrating a problem. And I've just made one up here. It's just a painter standing on a plank. It's supported at each end by vertical stands. So the plank has a length of 10 meters and a mass of 20 kilograms. And calculate the force exerted by each support on the plank. All right, so again, they seem a bit hairy and complex, these problems, but there is a technique that you can apply that will work every time. Just to let you know, there's no diagram provided at all. So whether a diagram's provided or not, I encourage you to do one. So I might just sketch one to start with. And so here's a plank, there's the support, there's the man. He's closer to the right end, I think it said, than the left end. Let's have a look. So the man is 60 kilograms, the plank is 20, the plank is 10 meters long. He's standing 2 meters from the right end. What's the force at that end? Pushing up, we presume, and what's the force at that end? Straight away, you might get an idea intuitively that the force at this end probably should be a bit bigger because the paint is standing a little bit closer to that end. Right, but now that we've got a bit of an idea, one of the strengths to doing a diagram is doing a diagram properly. I'm going to rub that out. Notice how we've just had a look at it. We've sketched a graph. You won't have a lot of time to do this in an assessment task, so that's why we're practicing it now. So I'm going to draw a bit more of a solid line, and that's just going to be representing the plank. And then I'm going to draw the forces acting, and I'm going to use a different color. So I might make FR at the right end, and I'm going to make FL. And these aren't necessarily to scale, but you'll notice already I've drawn FR a bit bigger. So the plank itself has weight, if you like, or a force due to gravity. I'm just going to label it as 20 kilograms. So that's 20 times G. The weight force equals mg. And the paint is standing 2 meters from the end. Here's 60 kilograms. So where will we put it? About here. It'll be fine. Remember, this is not to scale. 60 G. And then the distances become important. This is probably a fairly important part. At this point, we need to figure out where we're going to take torque. We've got to make a decision before we really go much further on this one. And this comes with practice. But the perspective of this video is what I'd really like you to pick up on. And we need to figure out at what end we're going to take torques about. Because there is two forces, we need to eliminate one of them somehow. And if we take torques about one end, the torque about that point will be 0. And I'm going to take it about, I'll just change color here to about this end, actually, the right end. And I'll explain why in just a moment. So I'm going to say the sum of the torques equals 0. And that's going to be clockwise. Clockwise about R. So I might put that in brackets. Clockwise about the right end. So before we go any further, we've got to put in the distances. So the paint is 2 meters from this end. And the plank, the weight of the plank is 5 meters from, because the plank is 10 meters overall. And the left pillar, of course, is the full length of the plank. And that goes there. So notice how I've just done them a little bit methodically. there. And I've gone the right end first rather than the left end, just a little bit of a trick. The distance is 2 meters from that end, whereas it would have been 8 meters from that end. So 2 is a smaller number. So it makes the calculation a little bit easier. These are just the little hacks we pick up with practice. So let's go. So we've got to account for 3 forces, 1, 2, 3, and multiply them by the respective distances. So FL times 10, that's positive because clockwise is positive. Minus, the other two are minus now, they're anti-clockwise, minus 20G times 5.0. Sometimes brackets helps, just keep these together. Minus 60G times 2.0, let's say. And all of that equals to 0 because it's in equilibrium. That's the idea. So now we have a linear equation with one unknown, FL, we can solve just using algebra. And just take care at this point. Even if you got the incorrect answer, you'd still be awarded marks for using the correct process. So I've got 10 FL. Notice I'm just keeping it moving a little bit, trying to emulate, you know, exam conditions if you like. So minus 20G times 5, that's minus 100G. I'm just consciously writing a little bit smaller, just because I know the space in an assessment task is fairly valuable. So 60G times 2, that's minus 120G. In fact, you know what I'll do? I'm going to make that an equals, and I'm going to make that a positive. All right. Just in real time, I'm just sort of looking to take a shortcut if I can. If you need to take more steps in the interim to get it right, that's okay. So that means FL equals it's 220G, which is 220 by 9.8. All right, I'm substituting that in, divided by 10. And if you run all that through your calculator, you're going to get FL is equal to 215.6 newtons, that'd be. So what I'm going to do, I'm going to round that to get F equals 2.2 by 10 to the 2 newtons. I'll put a box through in that as well. All right, so we've now solved one force out of the two. Remember the question, if we read the question, what's the force exerted by each support? So we've got to get the other one now. Now, what we could do is take talks about the other end if we wanted to, where most of it would be the same, except we'd probably redraw the distances. That would be 8 meters. That would be the main difference. But now that we've got one, we can employ the fact that the sum of the forces equals 0. And that just means the up forces equals the down forces. So I'll make up positive, and this way should be a little bit quicker. So FL plus FR up, right, remember up is positive. We've designated up as positive. So minus 20G minus 60G equals 0, because it's in what we call translational equilibrium. So that's rotational equilibrium. This is translational equilibrium. And both are required for what's called overall static equilibrium, or just equilibrium, okay? So we need to solve for FR, just circle that. And we've got FL, I'll just keep it as FR at this stage, equals, so 20G at minus 60G equals 80G. And I know what FL is, so I'll just put FR. And again, I'm just trying to write a little bit smaller so I can fit it all in. 80G minus FR, excuse me, FL, I should say, which was, now I'm going to use this figure actually, bit of a pro tip, use the unrounded figure in interim calculations. And if you do all of that, run that through your calculator. All right, just in the interest of disclosure, I've just planned this one out a bit. I've done this through my calculator. You should get 568.4. And that, or if we round that, that'll come out to 5.7 by 10 to the 2 newtons, to 2 significant figures. I'll just put a little bit of a box around it. You might be provided a box and that will be up. Now, just a bit of a tip. We would expect the right-hand one to be bigger than the left-hand one, and it is. So that's a self-checking thing we can do in real time. If we wanted to, if we had time, we could take the rotational equilibrium equation and do it around this end. And that should also work out. But that's basically it. There's two answers there. You've shown you're working out. Notice that for whoever's reading your solution, that you've told them what you're going to do. You know, you've talked about rotation. You can even put rotational equilibrium if you want. You don't have to. Equilibrium. We've used a bit of a shorthand, if you like, because time is valuable. Like this video has been going for about 11 minutes. You know, ideally we'd want to get that down to say 5 for the whole thing, 5-6 minutes. So at this point, I hope this serves you. They're a little bit complex, but they're doable at the end of the day with practice. So I hope that serves you. If you've got any questions about it at all, leave a comment. If you'd like to be coached through this and just have some practice walking through these, you can ask your teacher at school, or you can have a class with me as well, and I'll help you solve these. All right, thank you very much for watching another physics coaching video, and all the best with the rest of your preparation this week for your Unit 2 exam.